Okay, welcome to our talk on networking on the s390 architecture. Has several names by now, but s390 is the one in the Linux kernel. And of course, names. So, speaking of right. And yeah, the s390 architecture has a rich history. We built big boxes, and yeah, I can show you one of these boxes right here. This is the current generation. Can probably not tell, but there's actually two flavors of the hardware that are technically kind of the same hardware, except that sometimes you get blue highlights, as in this one in the photo, and sometimes you get orange highlights. And one is called IBM Z, and it runs all the flavors of operating systems we have on the platform: ZOS, ZTPF, ZVSE, and ZVM, and of course Linux as well. And then there's one version, which is maybe the only computer in the world that is restricted to running Linux, kind of. Linux plus the ZVM hypervisor, to be exact, and it gets orange highlights. Silicon is basically the same. We're targeting scale up in a single machine, and that means we have very big boxes. But you can start small. You can start with a 20U, which is probably still considered pretty big in the rest of the world. Interestingly, these systems are divided, which is also quite unusual. They have compute drawers that just do, well, compute with CPUs in it, and they have I/O drawers that just attach devices, including network devices and fiber channel and similar. And then you can go from one compute drawer plus one I/O drawer to fits in 20Us to 4 full-size 19-inch racks. So that's 4 compute drawers, 12 I/O drawers, and all those 4 compute drawers, there's still one SMP domain. So if you want it, you can put one Linux on it that sees all the CPUs and spreads across all 4 drawers. Can get from 4 cores to 200 cores. These are on the usable cores. There's a few more because we have called spares, and we have special offload cores used for different functionality. And we're also clocking pretty high. The air-cooled ones at 4.6 gigahertz. The water-cooled ones, which is really big ones, you can get at the same clock of 5.2 gigahertz. And which is another focus of the platform is reliability, availability, and purity to the max, meaning as best as you can get. We have hot plug for everything. You can remove compute drawers, evacuate the CPUs, and pull them out, replace them. You can replace memory. You can replace, of course, network cards, everything like that, without downtime for the machine. You can do firmware updates, microcode, all that stuff without downtime. We have these spare cores that I mentioned. They're for CPU hot sparing, where the CPU can detect that it is misbehaving and can be switched over to a spare CPU. We have PCIe link failure switch over, and yeah. And another important part that will play a role later is that we have always a virtualization layer that's minimum is logical partitions that name implies partition the machine, though you can have just one for the whole machine, also a partition, I guess. And these systems are direct descendants of the original System 360, which kind of, and might be a bold claim, kind of invented instruction set architecture, as in multiple machines with the same architecture, the same instruction set that was released back in 1964. Still has some compatibility to that, and the current generation of the architecture is called Z architecture, 64-bit now, and available since 2000. And these boxes are big endian only. Next slide. And I've already talked about the virtualization, like the minimum you can get. You see here on the right, that is a box that has just LPARs, logical partitions. You see here Linux 8 and Linux 9 run in these. Could have just two on one entire machine. We have on the left a bit more different flavors. You can have a logical partition running Linux with KVM in it. Normal KVM, as you know it from any other platform, can run Linux guest inside that KVM. Or the classic mainframe hypervisor, you can run ZVM. You see here Linux 3 and Linux 4 running under that hypervisor. And in LPAS, you cannot only run Linux. It's an IBM Z machine and not a Linux one. You can run ZOS as well, which is used very heavily by banks and similar institutions, and provides even more backwards compatibility for your COBOL programs from the 60s or what have you. And they can live together with Linux on the same machine. Next slide. And now for some things about Linux specifically on IBM Z and Linux One. Just organizational. I think it's very important to note that our kernel development has a long history. We've been have posted patches for supporting 390 systems back, and then it was still s390 back in 1999. And since then, we've always been doing mainline first development. Nothing goes into our supported Linux systems without being mainline first. If we need to backport something, we bring it upstream first. And we do have support in all major enterprise distributions. I'm not gonna name them, but you know who they are. And a few fun facts. I already mentioned we're big Indian, and it's not always fun because we are kind of the last big platform, at least the last one that has support in these enterprise distributions. I think there's still a few out there, other platforms that are big Indian, but as far as I remember, we're not supported in any of the distributions. Then another fun fact, 2024 last I checked, but on IBM Z, you can still boot Linux from virtual punch cards. And yes, you can boot a Linux 6.11 kernel when it comes out, and boot it from punch cards. And that's actually kind of a common thing to do, weirdly enough. And thankfully, it's virtual punch cards. I would not want to deal with that stack. We do have multi-level nested KVM, so you can run KVM, inside KVM, and so on. Don't do it though. Sometimes at some level, it's gonna get slower. We are probably one of the few platforms that has neither any frame buffer video output nor GPU support. And especially frame buffers, I guess, also weird. You can use a 3270 terminal. I don't know if who of you have ever seen these very green screeny things. It's not a lot of fun for a Linux console. It's not a good match with Xterm. Okay. The question was if that's the reason we're limited to 80 columns. I think it's 100 in the kernel now. Okay, next slide.
Okay, I think I take over from here. Can you hear me? Can you hear me?
Yes, we can hear you.
Okay. So Niklas was talking about all these virtual machines, first level hypervisor with logical partitions, LPARs, and second level with KVM and ZVM. So how do you connect them to the outside networks, and how do they connect to each other? Well, there are many options. So let us take you on a tour what we have networking-wise in S390. So starting with some basics, as Niklas said, Linux on s390 architecture basically looks totally the same as any other Linux for a user. However, when you look at the I/O, you see some differences, obviously, because there the hardware architecture shines through. So what you may see is that not all I/O devices are connected to PCI bus, but a lot of them are actually connected from a Linux point of view to a CCW bus. That stands for channel command word. That's what CCW means. And this concept actually dates back to the very early days of System 360, where I/O was punch card readers, printers, and then later it was disks and tapes. And they were connected via so-called channels that were sometimes even boxes with powerful firmware to the processing units. And very early on System 360, I think, they defined a channel architecture that provided an abstraction layer of all this I/O to the programs. So the program would always deal with channels and use channel command words to access the I/O devices. And the channels were quite intelligent firmware. They would handle a lot of the specialities of the hardware. And that provides compatibility over time. So you can add a new hardware model below and the channel will handle it and software doesn't have to change. The channel model also provides for virtualization that came very early on the mainframe. So the channel provides channel devices to all the different virtual machines that you saw on the previous picture. And that concept is in place today, even though in today's hardware that you see here below, the hardware is actually using PCI buses and PCI fan-out cards like any other hardware would do. But conceptually, to software, the interface is still a channel interface. And when the network cards came along and the idea that it would maybe a good idea to connect computers to each other into a network, first with token ring and then later with Ethernet, these network cards were also added as channels to the s390 architecture. So a network card is regarded as a channel and the virtual NICs that it connects to are represented as channel devices. And in Linux, this concept of channel devices is represented by the CCW bus that connects all the different devices. So in case of network, you can, for example, have a network card that is called OSA Express Open System Adapter, but that is a real card. And then you have QETH devices in the operating systems. The firmware in these channel cards is actually still quite powerful. So things like monitoring, probing, hot plug support, repair support that on other architectures a device driver may do, on s390, a lot of that is done by firmware, which makes sense because of the virtualization. If you have a hardware problem with a card, it's not the job of one instance to handle it, but it's the firmware's job to handle it. So that was all about general s390 I/O. Now back to our networking picture. You see a lot of QETH on this picture, and that is the name of one of the network device drivers. And actually, that is kind of our bread and butter device drivers. So most Linux on Z instances today connect via QETH to the network, either via OSA Express cards that are real hardware cards. In ZVM, it is very popular that ZVM emulates a network channel by its virtual switch, the ZVM vSwitch, and then provides channel devices to the ZVM guests. Or we have another type of virtual channel that is hypersockets. That is implemented in Z firmware and connects LPARs on the same machine, and is also represented as a QETH device to Linux. And the data is moved just by memory moves by firmware. So it's very low latency and quite high throughput. What you also see in this picture is that the architecture provides here a direct path from the OSA Express card into the ZVM guest. So the concept of first level and second level hypervisors, there's a lot of support in the hardware and firmware for that. So this architecture provides for address translation into the second level guests and also interrupt delivery into the second level guests. That is, there's hardware support in that. So this QETH, what does it mean? It's short for QDIO Ethernet. And QDIO is short for Queued Direct IO. So that is just the architecture definition that for networks and for FCP it's used as well. We use an interface that is based on queues. Well, big surprise. Ring buffers pointing to data buffers, just normal queues, which makes a lot of sense for a network card. And yep. And of course, again, these hardware interfaces, they are not only defined for the Linux machines running on s390, they are also, the hardware definition is also very often made for other operating systems like ZOS that use the same hardware and share this hardware with Linux because, yeah. Another thing about the QETH devices is that the first network channels on s390, they were actually providing layer 3 interfaces, what we call them. So they are basically IP devices in Linux. So all the MAC address, MAC handling, RPing, all that is offloaded to the network card, to firmware. And to the operating systems, IP interfaces are provided. That is still in use, and actually ZOS still uses that mainly. For Linux, it's not a perfect fit because the network stack expects an Ethernet device today, and many things like DHCP or so rely on Ethernet devices. So today, all these interfaces can be switched into layer 2 mode, as we call it, which means they represent themselves as Ethernet devices to the operating systems, and that is the way we mainly use them in Linux. As I said, the QETH driver is mainly our big bread and butter device driver. It has over the years many features, of course, not all hardware or virtual hardware provide all the features, and not all generations provide all the features. So there's quite a lot of code in there that we have to maintain. And we try in Linux, we try to map all these features in a way that suits Linux. So if possible, we try to map them to ETH tools and things like that are available on other network cards as well, so that they look like other Linux network interfaces would do, which is not always possible because some of these features were specifically invented for some special Z purpose, and then we may have sysfs interfaces, so whatever. So in this picture, not everything is QETH. Let me tell you about the other things briefly. We have KVM, as Niklas mentioned. That looks just like any other KVM, with one small difference. When we ported KVM and QEMU to the s390 architecture, they implemented VirdIO CCW as a bus layer. So in our KVM guests, we use VirdIO CCW instead of VirdIO PCI as a bus layer. Then we have interfaces that are provided by the ZVM hypervisor. One of them is CTC, and in Linux there's the CTC device driver for that. That stands for channel to channel. That's a really simple point-to-point connection. The hypervisor gives you two devices, you assign them to two guests, and whatever you put into the output buffer of one device will appear on the input buffer of the other device. Really simple, sometimes useful. Actually, in the old days, you could even have a channel-to-channel card and a channel-to-channel cable and connect two machines with that. That is no longer possible today, but it's still available as a ZVM feature. The other networking feature provided by the ZVM hypervisor is IUCV, for Inter-User Communication Vehicle. User here means actually virtual machine. And that goes back to the 70s, I think, when ZVM came up, the virtual machines were invented. And the idea was there really that every user of a computer, wouldn't it be nice if they all have the view that they own the whole machine, that they kind of have a virtual machine, that every user thinks they own the whole machine? And that is why user equals virtual machine still in the terminology in ZVM. And the transport is called Inter-User Communication Vehicle. That is a mechanism where you can send messages from one guest to the other guest, or from the hypervisor to the guest, or from the guest to the hypervisor. And the addressing is really simple. You just use the guest name to address wherever you want to send the messages. And the access control is done in the hypervisor. So that controls it. That is quite useful for things like consoles, where before you even have a network up and defined, you want to be able to send messages to a guest. For example, you could have a management guest that could manage installation of other guests and then use that as a remote console. And there's under drivers TTY HVC, there is such an implementation of a console. And there's other purposes for IUCV. As I said, IUCV is based on messages, so it's not really a device. It's not on the CCW bus. It directly uses messages. It's located in NetIUCV. There is an AF IUCV socket family. So you could write software with sockets and open AF IUCV sockets and use that mechanism to talk to the other guests on the same ZVM. There actually is today also under drivers S390 Net a NetIUCV network device based on this IUCV mechanism. But that actually we want to remove, and hopefully I get permission to send a patch from IBM to send a patch rather soon, because it just makes no sense. If you want to have a real network device, then go and define a vSwitch and a virtual LAN in your ZVM instance, and then you have a network device that works just like other network devices. IUCV is really makes more sense if you do not want to have a full-fledged network device, but just send simple messages. There's one more thing on this page, that is LCS, the LAN channel station. That one is really old. So the OSA cards that are connecting to the Ethernet, the network, before QDIO, there were already Ethernet cards available. And then people defined the QDIO architecture, and you can define your card with a firmware switch, what kind of firmware you load on it, whether it's an OSA or an OSE card. And if it's OSE, then it doesn't use queues. It just communicates via CCW messaging, and you need the LCS driver. And if you load your card with OSA, then you can use the QETH driver and the queues, which makes much more sense. But of course, because OSE was there first and we have to preserve compatibility for our customers, we had to drag the LCS and the OSE mode along until everybody made this transition. But as this is now almost 20 years, I think we can be sure that nobody is using these cards in OSE mode anymore, and we can finally remove the LCS driver from the network device drivers. So now back to Niklas. He will explain the remaining drivers and mechanisms on this picture.
Yes, let's go to the next slide, I think. Look into more detail. What we see here, MLX5, that's probably one term familiar to a lot of you. This is an MLX5 network driver as it is used everywhere else. No changes, just recompiled. With a small PCI layer, that's actually what I maintain, and it sits on top of a normal PCI virtual functions that comes out of a card that does these functions. We call it a Rocky card for reasons. But it's you can think of that it's a normal device which does a lot of driver things. And we do have, and I'm saying it's a native PCI device, but we also said before that we are using CCW instead of MMIO. And the fact is, we do not have real MMIO on the platform, never had. So what do you do if you want to do PCI but you don't have MMIO? Well, what disk architectures like to do, just make up an instruction. So originally we had a PCI store instruction, that's the first line here, but used the so-called PCI function handle, and the number of the PCI bar that you want to store into, as well as the length of the store, which I get is of course is a working way to do PCI, but it's a bit interesting, especially once you try plugging it into Linux, which only knows like read queue, write queue, IO read, IO write, and all of these just use addresses. So what do you do? Well, Linux makes up a virtual address and uses indirection to allow you to use read queue and write queue the same as you would anywhere else, allowing the MLX5 driver to run completely unchanged. But it's still kind of ugly. So in the 2 generations back, I'd say we added a new instruction, the PCI enhanced load store or MIO variant for memory IO. That takes a virtual address, still a length, and a register where you have the value that you want to store, of course. And this is still a special instruction, so it's not MMIO in the sense that you can use any normal store to store to an MMIO region. You have to use a special instruction, but at least the instruction takes the virtual address. You can map the virtual address just normal. And this is kind of designed for Linux APIs with keeping it the implementation cost a little lower. You can use IO remap, as I said, and we can even do reordering memory with IO remap, write combine. And still, this is, I think, the most odd part about native PCI on S390. But there's more, as the mandatory virtualization has some impacts. For example, we have the PCI probing done by firmware because, of course, the LPAR or KVM guest or ZVM guest does never see the entire machine unlimited, so to speak. So the PCI probing is done by firmware, and we do per PCI function pass through to those Linux instances. We also have the VF bars are mapped by firmware. They similar to how what other hypervisors will do, so that you can use an VF on its own. The right picture, those are VFs, so it makes sense that they can be used on their own. And we also have always an IO menu in all instances of Linux, be that in ZVM guest, KVM guest, or on LPAR. And and we have firmware interactions for various things. Okay, next slide. Okay, something about the network environment that I think shaped the reason for some of the follow-on things that I'm going to talk about. So with a very big box come a few interesting facts. For example, if you have 12 I/O drawers, of course you have hundreds of, or at least over 100 network ports. Those can have cables plugged going all kinds of places. You have over hundreds of VMs on one of those boxes, and they run on multiple hypervisors that run in parallel. Also something that I don't think is very common. You also do in-place updates, and here I don't mean like you don't have to shut down the machine, but in the sense of the customer buys a new version and rolls it into the place where the old one work is set, and replugs all the cables and expects the old operating systems that are booted from SAN to just boot up and work. And in almost all cases, external switches are customer owned and controlled. So this is very much not like a cloud environment. There's no software-defined networking. But of course, we're a single machine. So wouldn't it be nice if we could exploit the proximity when two systems talk to each other that actually end up being in the same machine? And so there's a couple of technologies for that. The hypersocket converged interfaces, which allow to automatically use the hypersocket internal networking when it's that they're or when you set it up that like two machines can either use internal or external networking. And then there's shared memory communications that I'm going to say a few more words on. Already shown here, there's two variants, SMCD and SMCR. SMCR you might know because it is available on other platforms. SMCD is, I think, less well known, but maybe more interesting because it tries to exploit the fact that two Linux systems or a Linux and a ZOS can establish a TCP connection and then and talk to each other. And wouldn't it be nice if you recognize, hey, we're on the same damn CPU or on the same damn chip? Why are we talking TCP? We can do memcopy. That's basically what SMCD does. During a TCP handshake, it helps to detect systems on the same footprint. And there's actually, this is coming to your laptop in the future, or run in Linux, because there's going to be, or it's already merged, the config SNC loopback that allows doing this between containers, for example. I think a very interesting development. And for SMCR, the idea is a bit similar in that two systems that talk to each other with TCP can detect, hey, by the way, I think we are on the same LAN segment. We know that switch there can do a Rocky v2. Let's just use RDMA. And this is not s390 specific, though. There is some convenience features. So far for SMC, you had to use AFSMC, the address family, to say, okay, I want to use SMC. It still allows you to fall back to TCP, but you had to make it immediately, had to use the address family. Now, I think in the network pull request for the upcoming merge window, it's already the IP proto SMC. That basically that's the same thing with IP proto, and you might think that doesn't really help me to do IP proto, but it turns out that this allows you to do this with BPF. I don't know. So the thing is, people don't want to change the applications, and so we so far provided an LD preload library that allowed you to just get AFSMC whenever you tried to do TCP. But now with IP proto SNC, you can instead use a BPF program that can do whatever BPF does to determine that it should apply this and use proto SMC instead of TCP/IP. Then you get this nice, hey, we are on the same machine, let's just do memcopy. Memcopy here is a memcopy by the hypervisor firmware, or rather by the machine firmware now. Next slide. Yeah, and I'm going to kind of wrap this up a little bit. I would like to say, I think we're, as the mainframe or s390 architecture or whatever name it has had over the many years of its existence, is alive, kicking, and I hope so. We're still innovating. I think we have a few or have challenges that either have always been common or sometimes have even been like experienced first in the mainframe area. Of course, we have large-scale virtualization, and I think it's also getting more common. Then we have challenges like increased network layering, where I think things like SMC can really help. As I said, for example, with config SMC loopback, you can have two containers with two different network namespaces, and all the infrastructure. You can, of course, have a lot of filters that allow or disallow connections. But once you have established a TCP connection, wouldn't it be nice if you can just bypass that if you know you're on the same kernel? And that's what SMC does. And I think it helps to kind of punch through the layers. So I think that's one answer to these increase in layers and containers, orchestrators, different hypervisors, or in our case, also two levels of hypervisors in some use cases. Of course, since this happens with the and we have other layers like VLAN, VXLAN, software-defined networking, and again, here SMC is something that can help use these layers for their partitioning or authorization activity, and still recognize when in the end you can take a shortcut. So, I think we also had, for example, for the virtualization, some unique solutions. We had, for example, this concept of shared NICs before SIOV was a thing. Nowadays you have that, and we also use it, as I said, for the PCI network cards. And yeah, I think we're continuing to modernize, and we are also, and this is also an interesting development. As you've heard, we have a lot of special things that are mostly historically grown. Like we ended up with channel devices not because we didn't like PCI, but because it didn't exist when it was introduced. And we are getting more standardized in, for example, the PCI-based network devices will become the default in the future. That's a statement of direction we have published. Especially for Linux, when it's running in Alpar or so, with less virtualization, we have VirtIO.net. By the way, nowadays also have VirtIO PCI. So while we started with VirtIO CCW, we also have VirtIO PCI now. We're also, and with the help of Alibaba, I should definitely mention, expanding SMCD to other architectures, bring these ideas to others. And yeah, I think sums it up. Questions?
So a couple of years back, at my previous job at Canonical, I implemented our bare metal deployment service on s390. And one of the really kind of interesting quirks I ran into early on is that by default on s390, the MAC address changes every time the link comes up. And I was able to get IBM to provide me with some config to change that. And I was just wondering, why do you do that?
It might be a question for Sandy.
Yeah, I can try to answer that. Well, you are talking now the OSA cards, and that is actually only true for the OSA cards connected to an LPAR, because hypersockets bring consistent MAC addresses, and the vSwitch and virtual LAN and ZVM also brings consistent MAC addresses. But the OSA cards, they do not have a mechanism. So nowadays, typically your systemd or whatever your distro provides a consistent MAC address, and it sticks with that. But the thing that the card itself does not provide a MAC address is still true for one flavor of the machine. We have another flavor of the machine now that has advanced hardware management. It's called Dynamic Partition Manager, DPM mode, and there you have hardware MAC management that manages the MAC addresses of all your OSA cards. So it is still true in some instances, but it's getting less and less.
So I'm just curious though, why was that implemented where the MAC address changes? Like, why not have consistent MAC addresses from the beginning?
Well, actually, it changes because of Linux. If the hardware does not give a MAC address, then you will get a random MAC address in Linux. That is the default in the network stack. And the OSA cards to the LPARs in non-DPM mode, they just do not provide MAC addresses, because if they are connected to 1,000 interfaces, how are they going to define the MAC addresses that the other OSA card next to it will not choose the same one?
I mean, I guess the same way Linux is generating unique MAC addresses.
Randomizing. Yeah, that would be a solution, but that is not the way it is implemented. The way it is implemented is that in DPM mode, in the advanced management mode, you have a MAC address manager for the whole machine that manages all the MAC addresses and makes sure that you don't have duplicates. And there you can also define, I want to use a certain prefix so that the other machine number 2 does not use the same MAC addresses, etc. So there is, in the advanced management mode, DPM mode, there is MAC address management for the whole hardware.
Okay, cool. Thank you.
Yeah, but that is a problem many people had, yeah.
Any more questions?